So now I'm going to come to the most outrageous suggestion. I've explained how much that complexity does, and I've shown you how complexity is what determines the direction of time. I'm now going to suggest that we should literally say complexity is time. So if we have n particles in Euclidean space, they will always form a shape. Look at the value of the shape potential, and I would let us say that is time. Now, it will run backwards in some Newtonian solutions. You saw it goes backwards and forwards, but it always is striving to increase. But for a large number of particles, as the number of particles goes up, I think it's going to be very rare. It's going to be very hard to find solutions where it runs backwards. So, and the complexity depends on two things, which is going to be very important. One, it depends upon the ratios of the separations between the particles, but it also increases with the number of particles. So I'm going to consider shapes, models of possible instantaneous shapes of universes of ever more particles that have a given value of the complexity. So I'm going to foliate shape space by isocomplexity surfaces, and you see that here. And take the value of the complexity and subtract its minimal value, and we're going to say that is the date stamp of each shape. So now these figures here have come out of shape dynamics and me talking to a very high-powered n-body specialist in Paris, Alain Albouy, and he got interested in the idea of seeing what these solutions look like, numerical solutions that look like as they come out of a total explosion. That's a very difficult problem, but what he did, for a few months he had a Spanish student, Manuel Izquierdo, finding the shapes of central configurations. And this shows here, one on the left, now it's in 2 dimensions, so the density is not quite uniform. It would be in 3 dimensions, and they look exactly the same in 3 dimensions, but they take vastly longer to calculate. So the one on the left is either exactly at the absolute minimum of the complexity. This is 1,000 equal mass particles, or it's very close to it. And the one on the right is only 0.5% larger in its complexity, but just look at the structure. And this was actually a very interesting discovery. Nobody before this had realized. Hitherto, when people had been looking to find central configurations, they'd either done what that paper by Batty, Gibbons and Sutcliffe and looked for ones very near the absolute minimum. So they found lots like the one on the left, or they did exhaustive searches for up to about 10 particles, and there's still several, because it's 10 factorial. So we're talking about thousands of central configurations if you have 10 particles. And they began to find beginnings of these incredible voids and filaments. But these central configurations that Manuel found it's a discovery. And it's thanks to the obsession of we-shaped dynamicists. And just look at it, it's quite extraordinary. Now, just imagine if this is in 2 dimensions, so you could have these balanced things, you could let them rotate with a certain angular momentum, and every 1,000 particles there would all, in a tremendous ballet, come in and out, breathing in elliptical motions around the center of mass. Online, you can find examples with 8 or 9 particles doing it. It's incredibly beautiful. But you would have 1,000 particles all coming in and going out around their center of mass, their common center of mass. Now, there's some things here that's very interesting. And actually, I will say I did actually predict it before this calculation was made. If you look at this, so we're going to ask the complexity to be increased. Now, there's a very easy way to increase the complexity, which is just to put two particles on the left closer to each other. That would immediately increase the complexity. It would leave a pretty dull structure. It's very easy to see by a Boltzmann time argument. So Boltzmann's great insight with entropy was, if you have particles in a box, there are vastly more distributions of the particles which look uniform than look non-uniform. And that applies here too in shape space, because shape space is effectively a box. But the dynamics in shape space, because of that one extra degree of freedom, is not Hamiltonian dynamics. So it's got this striving effect in it. So this changes the story. So what you have here, and you see it very clearly, is really remarkable, is instead of getting a dull Boltzmann uniformity, you get a very structured universe. And moreover, it satisfies the Copernican principle. Basically, it looks the same everywhere. If you take a small coin, a disk, and place it anywhere down there in that image on the right, basically you will have the same sort of structure as you'll find somewhere else. And there's, and moreover, that structure there, I would say it's a creative tension, and it realizes the atomist's dream of explaining all the macroscopic shapes we see in the universe by atoms. But they did it with swerving and solid atoms that you couldn't cut in half and hooks on them and so forth like that. These are just points, shapeless points, just points in Euclidean space governed by there. And I would also say it's Mach's principle for shapes on steroids. So Mach's principle tells you how the local inertial frames of reference are created by the relative motions of all the masses in the universe. Here you've got something infinitely more powerful. You've got a principle which fixes the shape exactly. It's a law of the instant. The whole shape is fixed. And in one of these things, everything is fixed, where every particle, all of its neighbors and how far the neighbors are away. And moreover, the same sort of thing is going to happen even if it isn't a central configuration, because you're always going to have that conflict between increasing the complexity, the creative tension between increasing the complexity, but at the same time, the Boltzmann effect, meaning that it's got to look the same everywhere. So you will go on going up like that. Now, there might even be, there's an interesting thing here, there might just be an explanation for non-Euclidean geometry, which is what Poincaré suggested. Poincaré argued that you can't just think about geometry on its own. You have to think about it, you have to specify geometry and the forces that act within that thing. And his argument was that maybe we would misinterpret Euclidean space for non-Euclidean space because of the effect of the forces. And Einstein has a nice paper on this from 1921. I think he says that sub spatiae eternitatis Poincaré is right. From the perspective of eternity, Poincaré is right. So maybe it's just there, because if you look, where you get a whole lot of particles together, close together, the separations between them are less than when they're not close to each other. So if you take the separations as being the measuring rods, that's just what you get in Einstein's theory of gravity near the sun, where measuring rods seem to be shorter, closer to the sun. So this is very speculative. So now just how I would define the Shannon entropy. Just take the largest separation in Manuel's thing on the right, and the shortest separation, divide them. Oh, by the way, just one other thing which was predicted was that all the shortest separations in the great bulk of all the shapes with a given complexity, all the shortest separations would be about the same. And this is exactly what you see in both of those, actually. And in 3 dimensions, it's even more accurate. So now take the shape, take the largest separation, the smallest, and that range there divided up into equal intervals, and those are bins for making a Shannon type entropy. And then you just look at all the two particle separations, measure them and put them in the according bins like that, and that'll give you a distribution of the things. And if it's a very dull one created by just in the left-hand central configuration, just putting two particles close to each other, the bin that has the smallest separation will only have one in. And that will tell you that you've got a non-Copernican universe. However, the one you're looking at there, my guess is that it will peak somewhere in the middle, and that will tell you that you've got a Copernican one. So my second state function is the Copernicity of there. And so the shapes with greatest interest will have a high Copernicity, and I do like checking etymology. The etymology of interest comes from to differ, to be important. All of this story actually came from a challenge that Pedro Ferreira, who apologizes for not being here today, but he's largely responsible for a lot of this, because he challenged Tim Kozlowski and myself to find an alternative to inflation in Newtonian n-body theory. And bit by bit, this drove us to consider these fabulous central configurations. So basically, the top left is the close to the absolute minimum of the complexity. That's very uniform. That would be the Big Bang. It's not a point. It's not where everything collapsed onto each other. It's a very, very uniform shape if the Newtonian theory is a guide. And there's some hope that the Newton one is right. Now, bottom right, that's a glassy distribution, or to the eye, it looks like what's called the Harrison-Zeldovich spectrum. And this is the sort of shape that you get, which is the supreme triumph of inflation theory at the moment, from which all structure in the universe is supposed to come at the moment. Now, inflationary theory does have its issues about whether it's right or not. But basically, I think you'll agree with me that if you start at the top left and increase the complexity, you're likely to come next to the one bottom right, which at least to the eye, without sort of doing all the Fourier transform to check what really is likely to come out, and it's much too early to say that, is actually like the key thing in cosmology, the Harrison-Zeldovich spectrum, from which all structure is believed to arise. Then left is a Poisson distribution. That's where particles just land at random and they come there. And a Poisson distribution is characterized by the fact that you get close coincidences, implausible coincidences, like those two unfortunate Malaysian planes, one that disappeared and one that was shot down within a couple of months of each other. That was typical Poisson distribution. And this just means that a Poisson distribution is going to be, if complexity is time, it's going to be in the very distant future.